We are going to discuss implicit differentiation, and it's a little bit different than what we've been doing because it's a technique of differentiation. So the rules were covered. We've done them all, and the functions we've done. But this is to deal with polynomial functions. Other functions are always y equals, and we want to know what happens when it's not y equals. So everything we've done so far, all the rules, and all the functions, the trig functions and the exponentials and logs and everything, have always been y equals something. And so the question is, what do I do if I know there's a relationship, but I don't know what it is in terms of y equals? Okay, so here's a question or an example. This is just an equation of a circle. It's centered at 0, 0, and it has a radius of 5. Not that any of that really matters to what we're doing necessarily, but it's a relationship. There is something that's going to happen when x and y move. They're going to move according to that formula. So there is a relationship, but it's not a function. Because if you think about a circle, right, it looks like, that's a really bad set of axes, but it looks like this. So it's not a function because it fails the vertical line test. That's hardly a vertical line, but you get the idea. So it's not a function, but it is a relationship, and it's called an implicit relationship because it's not explicit. In other words, it's not y equals. But what do I do to take the derivative of this? All right, and so here's what we do. What we do is we follow a two-step process, basically. We differentiate both sides with respect to x. We just take the derivative. This just means with respect to. All right, so with respect to x, so all we're doing is taking, x and x. But when we take the derivative with respect to x of a y function, so if I said, what's the derivative of y squared? What we do is we treat y as a function of x. So what we essentially say is this becomes a chain rule. So the derivative of y squared, you do the power, so it's 2y, but then you multiply by the derivative of y. So you treat it as a chain rule. And whenever you take the derivative with respect to x, anytime you take the derivative of y in that scenario, it's y prime. Okay? And it's important to recognize that. And that's because then the second step is to solve for y prime. Okay, so if we look at x squared plus y squared equals 25, and I say I want to take the derivative of this implicitly, the first step says take the derivative of everything. So the derivative of x squared is 2x. That's easy enough. The derivative of y squared we just did, it's 2y, and then multiply by y prime. And again, that's because it's a chain rule. We're treating y as a function of x. And so we don't know the derivative of y, but we're trying to find it. And then the derivative of 25 is 0. And so what we then do is we solve for y prime. So we get 2y, y prime is equal to minus 2x. And then we divide by 2y, so y prime is minus 2x divided by 2y, and that reduces to minus x over y. So that's y prime. And the difference you'll notice is that before, y prime only ever had x's in it. Now y prime actually has x's and y's in it. That's the difference with implicit differentiation. And these questions can get as complicated as you like. In other words, you can create this massive relationship or you can create smaller ones. It doesn't really matter. This is a relatively simple one, but the process is the same. So here's another example. All right. And actually, I'm just going to erase and then we'll go through it. So we're going to take the derivative of this. This function here, the derivative of that is just 12x cubed. Plus, then this is a product rule in here. So it's x cubed times the derivative of y, which is y prime, plus y multiplied by the derivative of x cubed, which is 3x squared. And then this guy, the derivative of y cubed is 3y squared, that's the power, and then multiplied by y prime, because again, we're treating it as a chain rule, and then the derivative of 36 is 0. So then what we do is we notice that has a y prime in it, that has a y prime in it. So I'm going to leave those over here. So I'm going to go x cubed y prime plus 3y squared y prime. And everything that doesn't have a y prime in it, so this guy and this guy, are going across the equal sign. So minus 3x squared y and minus 12x cubed. All right? And then, and that doesn't matter what side you put them on. Okay, you don't have to put them on one side or the other. It doesn't matter. You just have to put them on a side together, because what we're going to do then is we're going to factor out y prime. So we get this. And then what we're going to do, because we're trying to solve for y prime, is divide by that x cubed plus 3y squared. So you're going to end up with y prime equaling minus 3x squared y minus 12x cubed, all divided by x cubed plus 3y squared. Okay, and that's our answer. And I apologize for this being slightly tilted, but that's our answer. So you can get, again, more complicated if you wish. So we could add in some trig functions. We could say, what's the cosine of x plus the sine of y, and that equals, let's throw in a log function, log of base 3 of xy, let's say. All right. So let's say I want to take the derivative of this. And so the instructions will always say find y prime, or dy by dx. You might see that as well. So you might see it written as this instead. So if I want to find the derivative of cosine x, that's minus sine x. The derivative of sine y is cosine y and then multiplied by y prime. The derivative of log base 3, the derivative of that is 1 over xy ln 3. And then it's multiplied by the derivative of xy. So the derivative of xy is xy prime plus y, because the derivative of this is a product rule. So it's x times the derivative of y plus y times the derivative of x, which is 1. So then what you'll notice is, because I have brackets there, I have to just expand this. So I'm going to get xy prime over xy ln 3, and then plus y over xy ln 3. Okay? And this simplifies. I'll take the x out, and this simplifies. I'll take the y out. And so then I'm going to go minus sine x minus 1 over x ln 3. That's bringing this guy over. So I'm going like that. And then I'm going to bring this guy that way. So I'm going to get equals y prime over y ln 3 minus cosine y prime. All right, and then I'm going to check the time here. Then I'm going to solve for y prime by taking this y prime as a common factor. So I'm going to have minus sine x minus 1 over x ln 3. That stays the same. And it equals y prime onto 1 over y ln 3 minus cosine y. And then I divide. So I get minus sine x minus 1 over x ln 3 divided by 1 over y ln 3 minus cosine y. I don't really need brackets there, so I'll just get rid of that. But that's my answer. Now the problem with that answer, I guess, if you're looking at it in terms of what it looks like, it's not a very nice answer in terms of complex fractions. So if I want to simplify it, what I'm going to do is I'm going to multiply by xy ln 3, because that's the common denominator. I'm going to multiply everything up here by that, and I'm going to multiply everything down here by that, just to make it so that it's a little nicer. So I'm going to get minus sine, actually let me write it this way. I'll write the xy first. I'm going to get minus xy sine x ln 3, and then minus y, okay, because the x cancels and the ln 3 cancels, divided by x, and then minus xy cosine y ln 3. Okay, so that makes it so that it's all just one fraction instead of a complex fraction. So that's my final answer. Okay, and I want to make a distinction between this and simplifying. I didn't really simplify, I did a little bit, but generally what I did is just solve for y prime. So when it says do not simplify in the questions that we've been doing, it doesn't mean don't solve for y prime, or which would mean you would stop here, way back here, right? You could say I'm done, but you're not done until you've actually solved for y prime. So in theory, if it said don't simplify, you could stop at this point. But this is the sort of simplified answer. So that's logarithmic differentiation, or sorry, implicit differentiation. And we're going to practice a lot more of that in class, but that's the concept. So I'm just going to leave it there. We'll do more complicated ones, and hopefully you'll become proficient at it.